Hello, good day everyone. In continuation with our lectures with advanced theory of structures, we are now done with analysis of trusses and beams using matrix stiffness methods or matrix analysis of structures. But this time, let us go on or let's move forward with analysis of frames using matrix stiffness method. In this lecture series, we'll be understanding how do we solve frame structures using matrix analysis. So this is now frames on matrix stiffness methods. We are very familiar on how do we analyze in a 2D plane a particular frame, whether they are statically determinate or statically indeterminate type of frames. But in using matrix stiffness method, with using the matrix stiffness method, we will be able to solve those two types of uh, structures, either if it is statically determinate or statically indeterminate. This is both applicable on those manners. This is on some point without considering sideways, no? So matrix stiffness method. Another method on analysis is we have the approximate method on matrix stiffness, but we will only be covering the conventional method on matrix stiffness analysis on frames. So just like what we have here is a typical frame, with two members having two fixed supports, such as shown here, which has an unknown members, either if it has an applied load or an applied external joint loads. Now, first things first is for us to identify whether our frame is either statically determinate or statically determinate or indeterminate type of frame. After which, we will then assess the given frame, whether if it is subjected to a member loads or joint loads. Just like what we have here, an example of a frame with three unknown members having an equivalent member loads, or a frame that is subjected to a member loads, no? Any type of frame where any type of frame or any members within a given frame, as you can see here, if that will always depends on the orientation of the applied loads, will always need to convert those loads on its corresponding coordinate axis. So just like what we did in your theory 1 or an analysis of determinate frames as well as analysis of indeterminate frames, we always have to plot off the positive x and y coordinate plane of a particular member in analyzing a particular frame or a member of a particular frame. So after we have here a frame subjected to a member loads, always convert and identify the x and y component of such applied load in accordance to the set coordinate axis plane. Do not forget to assess your coordinate axis plane. Now, check whether your frame is now subjected to a joint load. So, a particular frame on each given joint should have three equivalent forces. The shear forces, the normal forces, and as well as the bending moments. No, always in any type of frames, rectangular, parallelogram type of frames, and so forth and so on, irregular shapes, any joints or within each member, there will always be shear forces, shear forces, and bending moments. And as we plot off our axis forces, always start with the normal forces, susunod yung ating shear forces, and lastly, our bending moment. So this particular frame is now identified with a subjected joint load. After identifying whether a frame is subjected to a member load or a joint load, we can then identify the fixed frame subjected to member loads, or the effect of a load on within a member on its particular joint connections. So as we assess and analyze a particular frame member, we'll always analyze them individually as a fixed member at both ends. Now, a fixedly supported at both ends. So, halimbawa, itong member natin, point B to point C, is loaded or subjected with a member load such as member load M, no? Analyze this member separately, assuming that point B and point C is a fixed support, or basically we will have to identify the fixed end moment of this particular member at both joint B and joint C. And that will always depend later on or on our near far node condition, and basing it on our analytical model of a frame. Again, do not forget, whenever we are numbering the axis forces and bending moments, always start with the normal force, next with the shear force, and lastly with the bending moment. And do not forget to assign your axis plane, your ordinate plane, your positive y and positive x, kung nasaan ba yung positive y and positive x mo. Yung positive x and y mo, depende yon sa orientation ng iyong near far node later on. So as you can see here, a frame that is subjected to joint load plus a frame that is subjected to a member load on its fixed frame is equal to a frame subjected to a member load. So how do we plot off the analytical model of a frame? Always take note of this. Whenever you are plotting the analytical model of a frame, always start your numbering on the joints which has a known displacements and unknown for known displacements and uh, start your numbering with known forces, I should say, sorry. Start your numbering with known forces and unknown displacements, no? As you can see here, our fixed support without any impending settlement or induced deformation or deflection are basically your unknown displacements, no? Then your joints B and C are your, of course, unknown displacement. But at those joints, there will possibly be a joint loads or applied joint loads. So again, always start numbering your axis forces and bending moments on joints which has known joint loads and unknown deflections. Okay? So pag fix, of course, walang deflection yan on X and Y and as well, X and Y and as well, tawag na dito, uh, tawag na dito, X and Y and as well as sa moment kasi fixed support naman yan. Then, again, do not forget to place your nodes and replace your joints, no? We have A, B, C, D. So we have 1, 2, 3, and 4. We have 4 nodes that will differ later on if a particular member have a tawag na dito, change in section. So halimbawa, si member 1 at 5 meters, ito yung kanyang section. Then after 5 meters, ito na naman yung kanyang section. So kagaya ng beams, every change within a span of a member, we will be introducing a imaginary joint there. Okay? So for this example, wala naman. So all throughout, pare-parehas yung kanilang section. And pare-parehas yung section within each member. So we have 4 nodes. 4 nodes. Then name your members. Following again the near far node condition. 1 to 2 is your member 1. 2 to 3 is your member 2. And 4 to 3 is your member 3. Okay? As I've already said kanina, start placing your axis forces and bending moment on joints which has known joint loads. Okay? Which has known joint loads or identifiable joint loads. So at Probably at node 2, node 3, there are applied loads there. And probably there will be a unknown deflections at those joints. And at node 1 and node 4, given that there are a fixed support, meaning there will be no deflection. Maliban na lang if we have induced or introduced a impending settlement or deflections on those particular nodes. But in this case, in this example, originally fixed support do not have deflections on both on both axial, shear, and moment. So basically, huli nating lalagyan yun ng axis forces. So starting with node 2, then node 3. Either way, parehas lang naman. So node 2, unahin si normal, susunod si shear, and last si moment. Moments are all in counterclockwise. Okay? Placing your bending moment are all in counterclockwise. So 1, 2, 3, 4, 5, and 6. 4, normal. 5 is shear. 6 is bending moment. Then kayo nang bahala doon sa mga natitira kasi fixed naman si node 2 and node 4. So with this one, 5, 6, 7, 8, and 9, 10, 11, and 12. In that manner, we can then simply separate later on our partition matrix that at the above section of our partition matrix where we could then solve the unknown displacements. Then the lower section of our partition matrix, we can then solve there our reaction forces, which are your 7 to 12. Unknown deflections are from 1 to 6. Okay? But if there are change in section within each member, introduce at the point of change yung ating imaginary joint, such as in this example. So after performing the analytical model analysis of our frame, meron na tayong analytical model, alam na natin yung number of members, yung near far node conditions, inclined members and non-inclined members, columns and girders and all that. Near far node, alam na natin yung axis forces, axial, shear, and moment. O nga pala, frame ang pinag-uusapan. So we will be dealing on three forces: axial, shear, and moment. Remember that on trusses, we only deal with axial and shear forces. But in beams, we only deal with shear and bending moments. There will be no axial forces on beams. Okay. On frames naman, again, frames considers axial, shear, and bending moment. After plotting off your analytical model, we can then start solving our matrix, start doing our matrix analysis by starting with our local stiffness matrix. So just like what we did with trusses and beams, start always your analysis with local stiffness matrix. So with local stiffness matrix, this is the actual effect of the loads within the member or within the axis of the member. Okay, so this will be our general matrix formula for our local stiffness matrix on a frame using matrix stiffness method. Again, this is on matrix stiffness method using fixed end moments, no? But it will differ later on if we're going to use the approximate method. So with member local stiffness matrix, ito yung ating local stiffness matrix using MSM on frames, whether they are inclined, horizontal, or vertical. Okay? As you can see here, we have the area of the section, the length of the member, and the moment of inertia, I. Then, again, yun lang naman. Hanapin nyo lahat yan. Modulus of elasticity of the member, moment of inertia, the length of the member cube, area of the section, length, then moment of inertia based on the given section of the member. Again, remember your numbering. So, ang ating numbering, first 3 rows is the near node. Then, the last 3 rows is your far node. First 3 columns are your near nodes, and last 3 columns are your far nodes. So, kagaya nito, with this local stiffness matrix, let's just say, yeah, member 2 ng example natin. Member 2, node 2 to node 3. So how do we number our local stiffness matrix? So that is 1, 2, 3, 4, 5, and 6. Just like what we did with the beams and trusses. So after identifying the local stiffness matrix of each member or of any member, we can then start converting the member from local stiffness matrix to its global stiffness matrix. On a member on a member under its local coordinate system, we could then identify there the end forces and end displacement based on its local coordinate system, such as shown in this figure. So this is how a particular member deflect and react on its local coordinate system. After converting, applying transformation method on this member, we can then transform it on the assigned axis, on its assigned axis or assigned coordinate plane. Assigned coordinate plane on converting it on its global coordinate system. We can then identify the x and y component, the x and y forces, the x and y displacement, and moments. No, member n forces and n displacement in the global coordinate system. So ay palibalik na rin lang natin yan. So from global, kailangan natin siyang from local, ita-transform natin siya into a global into its global coordinate system. So take note of those variables. Q, then F. Okay? Then V. So just like with trusses, yung U refers to the displacement on local coordinate system of a member. Yung V refers to the displacement of a member on its global coordinate system. Q refers to the end forces of a member on its local coordinate system. F refers to the end forces of a member on its global coordinate system. But how do we convert a member's local coordinate system, a local coordinate, into a global coordinate system? So conversion of local coordinate system to global coordinate system, or identifying our member global stiffness matrix. So kanina, meron na tayo nung ating local stiffness matrix. How do we convert the local stiffness matrix into a global stiffness matrix? By identifying the transformation matrix of each member, following always the near far node conditions. Okay? So this is now the transformation matrix of a member. So transformation matrix T, such as shown here. So cosine theta, meron kasi tayong horizontal, vertical ng member. Then meron din tayo ng length. Kung horizontal lang, so convert mo na lang siya, no? Cosine theta, sine theta, negative sine, cosine theta, ganon. Ito lang naman yung formula natin with transformation matrix. Then follow your numbering, near and far node. But we'll not be needing that later on. So computing for the end forces in local coordinate system, that is simply equal to the transformation matrix of a member times the end forces identified on the member on its global coordinate system. Computing the end displacement in local coordinate system, that is equal now to transformation matrix of the member times the end displacement in global coordinate system. And either way, if we're going to solve the end forces on the global stiffness matrix, global coordinate system, that is simply equal to the transpose of the transformation matrix times the end forces on the local coordinate system, the end displacement on the global coordinate system is equal now to the transpose of the transformation matrix times the end displacement of a member on its local coordinate system. Okay, after plotting or solving for the transformation matrix of the member, we can then now solve for the member global stiffness matrix. Solving for the member global stiffness matrix using the shortcut or the formula that is basically the product of the transpose transformation matrix of a member times the local stiffness matrix of that member times again on its transformation matrix. Again, solving the global stiffness matrix of a member is simply the product of the transpose transformation matrix times the local stiffness matrix times the transformation matrix of that member. Pero kung ayaw mong gawin yan, ayaw mong kunin yung transpose, yung local, yung and so forth and so long, but you will be needing them later on in solving the end forces and moments on both local and global coordinate system. You can use the general formula on global stiffness matrix with MSM of frames or matrix stiffness method on frames. So this is now, or this will serve now as our general formula in solving the global stiffness matrix of a member with frames. So again, that is a 6 by 6 matrix. No, 6 by 6 matrix. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So napakahaba. And do not forget your near far node number. Same goes with the columns. No. Again, the first three rows are your near nodes, starting with normal, shear, and moment. Then the last three rows, again, is your far node, starting again with normal, shear, and moment. Same goes with columns. First three columns is your near node, and the last three columns are your far nodes. Always start with normal, susunod si shear, susunod si moment, then susunod again si normal, shear, and moment. That is a 6 by 6 matrix. No? After identifying your global stiffness matrix of each member, just like what we did with trusses and beams, you may now summate the global stiffness matrix to identify our general global stiffness matrix, or simply your structure stiffness matrix of a frame. So within this frame, probably there are 2, 3, or 5 members. So given that there are 5 global stiffness matrix, so summate them column to column, row to row. So parang yung ginawa natin, 1 is to 1, 1 is to 2, 1 is to 3, 1 is to 6, and so forth and so long, 2 is to 1, blah, blah, blah. Yeah, just like what we did with trusses and beams. No? So summation of all global stiffness matrix of a frame is simply our structure stiffness matrix. Then from there on, you may start adding those dashed line to identify your partition matrix. S11, your S12, your S21, and S22. Your horizontal partition matrix refers to the number of rows where there are unknown deflections or unknown displacements, no? Ganun din si vertical. So, pababa, hanapin mo yung ilang number of deflections. Halimbawa, merong 5 number of unknown displacement. So, magbilang ka ng 5 row, then 5 columns. Then, yun na yung magiging basis mo for your partitions. So, if we have 5 unknown displacement and also 5 unknown forces, so 5 by 5 yung ating partition. If it is a mga ganon, no? So after performing or plotting your structure matrix, we may then start finding our fixed end forces on its local coordinate system. So just like what we did with beams, kailangan nating isolve yung fixed end moments or fixed end forces on our member on each of our members based on those applied member loads, no? So that will be on our next lecture.